Greetings, wonderful college physics students. So I made this video here to help you out with your homework under Unit 1. This is the third homework assignment. We're going to chat about numbers 1, 2, 3, and 4. Okay, let's start with number 1. It says something about an ant crawling along. And you always want to start all of these with a picture. The sketch I'm looking at looks something like this. And this is a position like x, y coordinate. And the ant is starting about here. I'm just going to draw a dot. There's a velocity vector given. And in the example that I have here, that I'm going to call that V1, that's 0.13 meter per second. Your numbers will probably vary. And that shows the ant kind of doing some sort of squirrely path here. And then there's a final velocity vector drawn, 0.13 meter per second. Again, your numbers probably will be different, so always start by drawing a picture. Now these positions are given here. I'm just going to put y1 and x1. These are numbers that are in your problem. And then we've got an x2 and a y2. Again, these are numbers that are in your problem. So when it says to calculate the displacement, part A, where it says delta x, right? So delta anything is x final minus x initial, and your x final is this number, and your x initial is this number. Delta y, you calculate it virtually the same way. It's just that you're using the y2 and the y1 to get your delta y. Okay, part B, where it says average velocity. Now it's got like a V, it says AV, which is, AV, which is for average, comma, x. That's a heck of a subscript, but I would just put velocity x with a bar. That means average. And that's going to be delta x over delta t. And the delta x you're going to get from up above. And the delta t's are given in the directions if you read it. I'll just say that this you can get from your directions. All right, part B, average velocity y direction. You're going to calculate the same way. That's going to be a delta y over delta t. You're going to get the delta y from here. Same delta t as before. Part C, where it says to find the average acceleration. So you're going to have an average acceleration. Again, that's what that bar means, in the x direction. Take your change in velocity in the x direction over your change in time. Now you're going to have to calculate this change in velocity in the x direction here. Your change in velocity in the x direction is going to be your initial velocity, your final velocity x direction minus your initial velocity x direction, and whatever this is, that's your final velocity x direction. And you'll notice here's our initial velocity, but it doesn't have an x component. So this you're going to get from here. This is 0, assuming you got a picture that looks like mine, and then you're going to divide by delta t. To get the acceleration, average acceleration in the y direction, that's going to be change in velocity over change in time. And again, this will be only y components. And your final velocity, if you look right here, does not have a y component. So your v final y direction is 0, and your v final y direction is 0 because this does not have a y component, and your v initial y direction is this number, whatever you have there. So that should get you through that problem. All right, let's chat about number 2. All right, an airplane holding a pattern flies at a constant altitude along a circular path with a given radius. The airplane does a half circle. All right, so again, start this with a picture, just like about every problem here. Let's say, here's my airplane top view. And let me do this. Get a couple more of those. Copy, paste. Save this for a minute. What this airplane does is it says something about flying in a half circle. So now let me put this over here. Good enough. Right, so here is our initial starting point, and here's our final point. And the radius was given in the problem, right? So the radius of the circle, like here's the center, is like this distance. So this distance in green right here, I'll do this, is twice your radius. Now you'll notice I put an arrowhead on it. That's because this is now a displacement vector, right? Here's our initial position, here's our final position. So this vector represents the change in position of the airplane. I suspect that'll be relevant later. So part A, determine the magnitude of the airplane's displacement. Okay, that's this distance, and I'll let you answer that. Part B, determine the magnitude of the average velocity. All right, so velocity is a vector, and sometimes we write it like delta x over delta t for a one-dimensional motion along the x direction, or sometimes we write velocity as delta y over delta t. That's for motion in what we would call the y direction. In two-dimensional problems, sometimes we say that your change in your velocity, your average velocity, is change in some position vector. I usually call it r over a change in time. In this example, this right here is your change in position from here to here, right? Your delta r is some distance, some magnitude, and if I were to attach a unit vector to it in the j direction, and again, a little bit about unit vectors. Remember x, y, and I points this way, j points this way. Right? Then when you calculate your average velocity, take this and divide by time. Right? Part C. Now, C asks a slightly different question. It says to find the average speed. Now, speed is not a vector. It's just distance over time. And there's a big difference here between the change in position of the plane and the distance traveled. The green vector is the change in position. That's called a displacement. That's a vector. In blue, there's your distance traveled. This distance right here is the blue, and that's not a vector, and that's half a circle. Remember that the circumference of a circle is 2 pi r. Half of that would be pi r. That should get you through with number 2 there. Let's chat about number 3. This stuff is exciting. Whoops. Get rid of this. Let's see, it says a hiker walks 1.8 kilometers north and then 2.25 kilometers east, all in 4 hours. So start by drawing these displacement vectors. 1.8 kilometers north might look something like this. 1.8 kilometers. Now that's an example of a displacement. That's a change in position. If you wanted to, you could call that 1.8 kilometers plus j direction in a standard x, y coordinate system. Then they walk 2.2 kilometers east, all in 4 hours. All right, so the 2.2 kilometers east, we might add a vector for that. Now I'm not going to do this like get a ruler out, but if this distance is 1.8, 2.4 would be considerably longer. So our net change in displacement, that's this vector. I usually call that something like delta r. So when it says calculate the magnitude and direction of the hiker's displacement during this time frame. So the magnitude is the length of this vector, and in this example we can do that by Pythagorean theorem because this is a right triangle. When it says the direction, now it says north of east. In my picture, if this is east, this is the angle they're asking about right there, which by the way is the same as this angle. And you can find that using the tangent function, inverse tangent of 1.8 over 2.4. Part B, calculate the magnitude and direction of the average velocity. All right, so this is just a two-dimensional problem. There's a couple ways we can work this, right? Here's, I guess, how I would work it. Your average velocity, right, is equal to the change in your position vector over change in time. And this is equal to 2.4 I plus 1.8 j, and I'll just put the units out here in kilometers. And then just divide this by time, whatever your time is in the problem. This was given. And I probably would do that in time in hours, and that'll give you, you'll get an x component, and that number will have units of kilometer per hour in the I direction. This number will have units of kilometer per hour in the j direction. Okay, part C. When you calculate the average speed. Now remember, speed is distance over time. That's not a vector. I'll do this in blue again. The distance traveled, right, this person was walking, they walked 1.8 kilometers this way and then 2.4 kilometers this way. So this thing is the sum of those two distances. No unit vectors because distance is not a vector. So that should get you through this one. Let's chat about number 4. Let's see, a miniature chopper at given coordinates, right? So when you work these, right, start with a picture. And I'm just doing quick sketches here, quicker than usual even. It's your homework, not mine. All right, there's an XY coordinate system. A chopper starts at a certain X and certain Y given in the problem. I'm not even going to bother writing them down. Yours are likely different anyway. They gave me an X1 and a Y1. These are numbers given in the problem. Then they tell us an average velocity of 1.7 meter per second I minus 2.5 meter per second J. Now they didn't write it quite like this. What they gave you is the, it says this, quite a subscript here, VA V comma X. Okay, that's quite a subscript. That's what this means. They're talking about average velocity x direction. The shorthand for that is this, average velocity x direction. And by the way, it's an initial velocity. I would also tack an I on it. Could have actually tacked an I up there as well. Now that's getting to be too ridiculous for a subscript for me, but anyway, this is the x component of the velocity vector, right? Then you were given a VAV y, crummy writing, VAV, average velocity y direction. This is a number given in the problem. This is the y component of your initial velocity vector. So all I did is I took the numbers given and I gave them directions by attaching unit vectors to it. Meaning that if we get back to this picture, at the instant shown, this object is moving maybe something like this. There's the initial velocity vector. I'll call it V1, right? It's got a positive x component, a negative y component, and that y component's a little larger than the x component. That's why I drew it about the way I did. Let's see, part B. What are the x and y coordinates a few seconds later? So, right, two-dimensional problems. There's a couple ways to handle this. We can either do it like one step at a time, something like this. Your velocity in the x direction is equal to delta x over delta t. This is the 1.7 meters per second. Put in the time. That will tell you the delta x. Your velocity in the y direction is equal to delta y over delta t. This you're going to get from here. Put in the delta t, that will get you the delta y. Now, these deltas here, they don't actually tell you the answer, if you will, because the question doesn't say to find the delta x, it says what is the new x coordinate. Right, so I'll call that like x final. Well, that's going to equal your x initial, that's this, plus your delta x. Same thing with y's. So that should get you through that one as well. I hope that this helps you get your homework done. Have a great day.